Hi, welcome YouTube. This is my very first lesson on the computer fundamentals. I'm at the University of Nottingham, Ningbo, China. It's the University of Nottingham's China campus. And I work at the School of Computer Science, where we recently, in the recent 2 years, introduced a new book and a new module called Computer Fundamentals, based on the Nand2Tetris website and this particular book. And over the last 2 years, I've discovered that it is quite important that students learn this, especially computer science students, because in the past, most computer science or computing students, say 20, 30 years ago, they would know how computers work, but rarely today, as computer science abstracts from the hardware. We are left with a black box where students have no idea how the internal works, how Boolean logic builds up to different high components and to memory units and so on. So whilst also looking online as a module convener, I realized that there aren't actually many tutorials, video tutorials that are based on this book. So I'm going to have to do one based on a request from my students, but also as a guide to many computer science students in the future. So this book, The Elements of Computing Systems, Building a Modern Computer from First Principles, Nand2Tetris Companion, there's a website, and you can visit that. I'll put it down in a link below. And the book's by Noam Nissan and Shimon Shok, and I hope I pronounced that correctly. And it's a very good book, and the guide, the hardware simulator, software, and PowerPoint slides, they are very, very useful. But I will not particularly be using the PowerPoint slides as an accompaniment of the book and the website. I'll be having my own PowerPoint slides as my principle of teaching. So this book has, let's see, various chapters, as you can see, right? So particularly the first 5-6 chapters I find extremely useful for beginners in computer science, and I will be covering a series of video tutorials based on the first 5-6 chapters. So stay tuned. Okay, this is the introduction to computer, base 10 and base 2 number systems, binary numbers and representations, bits and bytes, building a digital picture, textual representation, bits for computing information inside the computer. So these are the very brief lectures that we're covering today. And when you look at the computer, many people essentially just use it. You have a user interface such as a keyboard and a mouse. But the problem is, how does things work? For example, it is a black box. So is there any complex piece of equipment, typically a unit in an electronic system, with contents that are mysterious to the user? And most users, you find that even computer science students do not know how a computer system works. So it's a University of Nottingham in Ningbo, China. So rather than using the YouTube video, I use the Youku Chinese version of the equivalent of a YouTube website. How does things work? When you send a message either via WeChat or WhatsApp or any kinds of messengers, when you type in the text, what actually happens inside the computer system? When you change a font size in a Microsoft Word document, when you play videos or when you play computer games, how does a computer system actually simulate all the characters, 3D environments, and so on? This is a very mysterious subject. But we're going to have a look at how things work from a very basic level. How does it work? What's inside? When you plug in a computer, what happens? Now, the foundation that built up the computer can do very simple things. Actually, very, very simple, and we shall see how simple it is. But the combination or interaction of simple things become complex very quickly, such as an atom, interacting with other atoms and molecules, building up, into a biological cell, and biological cell works together. It becomes increasingly complex. Then you have a complete enclosed system such as a human body, and you have a society, you have a community, and the world population, businesses, economics. They're all built from very simple things. A computer computes information. It computes bits, which are actually binary digits. And we'll have a look at this example. We have 10 fingers, so we are actually calculating using base 10 numbers. Once we have a 10, then we increment, and it becomes magnitude in that order. And that's, computer really have 2 fingers. That's why, it uses the binary base 2 number system to calculate information. So we use base 10, we'll have a look, right? If we were to calculate with base 10 for 3, 4, 5, 6, we have 3, 4, 5, 6. And we can actually break this into smaller components. So we have 6 ones, 5 tens, 4 hundreds, and 3 1,000. So this is positionally weighted. Actual value depends on the position. So we look at, break this apart, and we look at this, 6 ones, 5 tens, 4 hundreds, 3 1,000s, and that adds up to that number that we saw earlier. Okay, so this is what it looks like. Now we can also change this slightly, so we can multiply in this way: 6 times 1, 5 times 10, 4 times 100, and 3 times 1,000. If you look carefully, you can see that this is a 1, and then you have 1 0, 2 zeros, 3 zeros, and guess what? If you go up to the next number, it will be 4 zeros, and so on. So that can be changed, and you can have a look. This is no zeros, 1 zeros, 2 zeros, 3 zeros. So it's actually a power of the base 10 number, right? Added together to have that number, right? Let's take a look. Right, so this is incrementing 0, 1, 2, 3. So if you see that pattern, everything becomes easy. Everything becomes easy. So let's move on. Right, let's move on. 1 plus 1 in base 10 number is not 10. So this has got to be the binary numbers. Right, so 1 plus 1 is 2, and there's an equivalent of the binary number 2. We'll look at a base 2 system. For this particular number, it is 5. How do we get to that number? How do we get to that value? So we have a look. So we have 1, right? 1, 2, 0, 2s, 1, 4s, 0 times 8. Right? If we look at this, we can see that this also, as the base 2 number, also increments. So 0, 1, 2, 3. Okay. Now, but this is a base 2 number, so we're going to have to multiply our binary digit. Okay. That bit is 1, so it's switched on. Okay. And this is 0. When you multiply by 2 to the power of 1, you get 0. Right, and this is 1 again, you multiply by 2 to the power of 2, 4, you get a 4, and so on. And that if you add all this up, it becomes 5. Right? It becomes 5. And that's a base 2 number system. So why does a computer use a base 2 system? 0 and 1. These are the questions that you should be asking. How does an electronic circuit with only combinations of 1s and 0s to store, compute, and represent data? How does it work? How can you digitize media, turn what we see here into something that can be represented within a computer using only 1s and 0 states? So let's come back to the binary system, we'll say that our binary systems are basically switches. This is switches, right? So if you turn this on, then the numbers added up will be different. But since the switches are off, 0, then anything multiplied by 0 will be 0. Okay, so that's the result. On the other hand, if you switch this on, okay, and this is off, this is on, this is off, the combination of this adds up to 5. Okay, 0 plus 4 plus 0 plus 1 is 5. So this is 1. Okay, if it's switched on and you multiply by the base 2 calculation, it's 1. This is switched off and you multiply by that, 2 is 0. This is switched on, okay, multiply by 4, it's 4. And this is switched off, so it's 0. And that adds up to an equivalent of 5. Right? So binary number system is essentially a switch, switching off and on, right? With a base 2 calculation below where you multiply with the switches and you get the results and you sum them together. That's how it works. Very basic, okay? And the result is 5. So looking at an 8-bit system, and this obviously is incrementing. The power is incrementing, as you can see. 0, 1, 2, 3, 4, 5, 6, 7, and the base is 2. So this is all off, so the result is nothing. But let's look at an example. Once we switch this on, so the binary number is 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1. Okay? Once we start to switch on the bits in an 8-bit system, we can start multiplying. So if I multiply this by this, I get a 1, so the power of 0 is 1, and that's a 1. And this is switched off, 0, switched off, 0. Okay, and this is switched on. So we multiply 1 by 8 to the power of 3 is 8. We get an 8. For this, we get a 16. 0, we get a 64. And if you add that all together, you get the result of what this binary equivalent is to a base 10 system. Let's look at binary numbers and representations, bits and storage capacity. Now we know binary systems, we can use it for counting. Okay, we can convert between binary and the base 10, binary and decimal numbers. But how do we actually use this to store data? Data is very important to a computer, to any information system. Data is quite important. How do we actually use this to store information, to store data? So have a look. Okay, so in a 2-bit system, right? How many different combinations can you get out of base 2 system, right? So this is 0, 0, 0, 1, 1, 0, 1, 1, and we have exhausted the combinations. Okay. Now, so this means that in a 2-bit system, in a 2-bit system, we can have 4 different kinds of data. Am I right? Okay. So, for example, you may decide to use 0, 0 to represent A. You may decide to use 0, 1 to represent B. You decide to use 1, 0 to represent C. You may decide to use 1, 1 to represent D. And that gives you 4 kinds of data that can be represented by a 2-bit system. On the other hand, you may use this to represent numbers. So this will be 0, 1, 2, and 3. Okay, so it all depends on what you want to represent using what sort of data you want to represent using the number system. Okay, this could be emoticons. You could use this to represent an emoticon of different types, and you have only 4 types. So 2 bits can make 4 states, because 2 to the power of 2 is 4. Okay, base 2 to the power of 2 is 4 patterns. Now we can actually assign meaning, as you can see, as I covered earlier. Okay, symbolically we can assign that particular data to these particular numbers, and we can also have the actual decimal number. Now the question is, if you increase from 2 states, right, to 4 states, right? What happens? If you increase this to 8 bits, okay, this is 2 bits. If you increase this to 4 bits, if you increase to 8 bits, if you increase this to 16 bit, 32 bit, 64 bit, what happens? Which means it means that you have more patterns to store data with, and that's how simple it is, right? That's how simple it is. So 8 bits. Let's have a look. 8 bits, you have 8, okay, bits. 8 to the power of 8 is 256. So this means that you can have a combination of 256 patterns. And 256 patterns is definitely more than the number of keys you have in your keyboard. So 8 bits is more than sufficient to contain your ASCII characters from capitalized A to not to A to all the way to Z, numbers, punctuations, and so on. There's so many symbols you can represent in an 8-bit system. So the higher this is, the more data you can represent, the more data you can store. That's how bit works. So modern computer system, is no longer 32 bits. It is 64 bit. Even the majority of your smartphones are in 64 bit mode, a 64 bit system, which means that they can contain a lot more data than an 8 bit or 2 bit or 4 bit system. So the larger number of bits, the more information you can hold. So we'll have a look. So 1 bit is that, 2 bits, 3 bits, and so on, up to 8 bit, which is 1 byte. Okay, so the bits is binary digits. 1 bit can only contain 2 states, 2 bits, 4 states, 3 bits, 8 states, 8 patterns, and so on. Okay, up to 8 bit, 256 patterns. And 2 to the power of 2, 4 states, you will have 4 patterns. There's a combination of the states and places. Okay, so I hope this means something to you, but let's go on. So I've covered this earlier. 8 bits is 1 byte, 16 bits is 2 bytes, which is 1 word, and then you have D word, quad word, and so on. Okay, 64 bits. So it's 8 bytes. Okay, and this is one chunk of data that your modern computer system can take. It's 64 bits. Okay, it's quad word. Now, using bits and bytes, how do you actually build a digital picture? Right? So we've covered text, right? 8 bit of information, 8 bit. In a system of 8 bit, we have 256 combinations, 256 patterns. How can we actually build a pixel, right? We'll just have a look. So this is building a digital picture with coordinates, dimension, and pixel depth. And let's say that our pixel width is 800. So if you count this 800 pixels, this is 600 pixels. Okay, with the height and the width, and the origin starts from here. So we can actually move pictures around. Okay, so 200 pixels to the right, 200 pixels downwards, and that we put our picture. Okay, and our picture size can be of this particular width and height. Now, if we zoom in, and we zoom in further to look at one pixel, each of these pixels has a bit depth describing its color. Now, if a pixel has 1 bit, which means that it's either on or off, so you can actually represent only 2 colors. Yeah. So early computers, for example, my Apple II in 1984, it was in either green or it's in black. So green is when the pixel is switched on. So that's 1. Black is when the pixel is switched off, and that's 0. But we can definitely represent a pixel with more than 1 bit. Am I right? We can represent it with 4 bit, which is more color. We can represent it 8 bit with 256 colors. We can represent it with a lot more, 16 bit, and so on. So the bit depth is made up of bits. Now if we look at color depth, the amount of data stored per pixel determines the depth, number of grayscales or colors that can be displayed, bits per pixel. So in a 1 bit depth picture, look, it's either switched on, white, or switched off, black. And the combination of that, okay, so the density of the pixel makes it either whiter or gray, it appears gray, and then or it becomes black, right? So this is quite creative. You can actually use a 1 bit system to represent sort of a grayscale, a simulated grayscale. But there's really only 2 colors here. If you look, right, black or white, and the density of the white makes it whiter. So that's the difference. Yeah. In a 4-bit depth system, see the color is much more. It looks much better. But still, the transition between one color to the next is clearly defined. So this is not exactly very nice. If you increase the bit depth, okay, your color essentially increases, right? Increases, and that makes a beautiful picture. If it's a 16-bit picture, it's of a much higher, much greater color range, and that builds a better picture. So a pixel is represented by color depth, which is actually the bit depth. Okay, then red, green, blue, and combination of that becomes a different color. Now, so if we look at an 8-bit pixel with 256 color, frequently if you are a web developer or designer or you use Photoshop, you can see the color, web color, okay, 256 colors, and these are all the colors that we can represent on screen. Okay, but we can actually increase from 8-bit to 24-bit, which is true color, and so each pixel is represented by 24 bits. So if you count this, right, 8 times 3, 8 bits, 3 times 8 bits is 24. So we have actually 24 bits. And with each 8-bit, we can represent blue, green, and red. And when you combine that together, you have a special color in the color range. And this smoothens the color transition from one to the next. Right? So at this point, we understand now how bits can be used, right? Not only to represent ASCII characters, but it can also be used to represent pixels. And that that's how we simulate, right? That's how we digitize pictures into the computer. Again, coming to the character set, this is the American Standard Code for Information Interchange. The text representation, if we have a 8-bit system, we can represent 255 from 0 to 255. So we have 256 representation, and you can see we have capital alphabets. We have the small caps A all the way to Z. And so essentially a character code is a mapping which defines a one-to-one representance between characters and a set of numbers. And this number, so this is actually in 8-bit, it's 1111, 1111, 8 ones. And this is essentially now spacebar is 0. Okay, this is how we represent textual information using bits. So we've reached the end of our lecture, and the next one in line after this video is bits for computing information. So far we've seen how we can use a binary system with 8 bits or more or less to store data, to represent a unit of information. So it's 8 bits, we have 256 patterns, and that can be used for ASCII, for example, or if it's 8-bit, we can use that for storing bit depth information for the pixel on the screen. So this is the end of the tutorial, and we've seen how we can use a combination of bits to store information. Now you should actually really ask, how you can use bits to construct logic gates so that we can not only store data but also compute information. and that will be the next series of videos. So thanks for watching this video. If you like the video and you'd like to receive more videos as such in the future, please subscribe and also like and give your comments. Thanks.